Hi, today we're going to talk about trig derivatives. So I'll give you formulas, give you examples, we'll have lots of fun. Well, maybe not so much fun, but it's not so bad. We've done these two before, sine and cosine, at least sort of. We graphed it and looked at the slopes, came to the conclusion the derivative of the sine is the cosine. The derivative of the cosine, we tried that, it turns out to be minus the sine. There are proofs of this. You can use the sum of angles formulas, break it apart, use trig limits, and both of these work out tremendously well. But the more interesting ones, I think, are these, because you can write the tangent in terms of the sine and cosine and use the quotient rule. Let's do that. The tangent of x is the sine of x over the cosine of x. So if I take the derivative, do you remember the quotient rule? The derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So we get cosine of x times cosine of x minus minus, so plus sine of x times sine of x over cosine squared of x. You could do a lot of things with this. You could write 1 plus, well, that's the tangent squared, but the top here is actually 1 because the cosine squared of x plus the sine squared of x is 1. Now, 1 over the cosine squared of x, hopefully you remember your trig. 1 over the cosine of x is the secant of x, so we're squaring, so this is just the secant squared of x. Likewise, if you do it all out, the derivative of the secant is the secant of x times the tangent of x. Now, the cotangent is just the flip of the secant of the tangent, and the rules work out pretty well. What you end up with is the cosecant squared of x, but with a minus sign, and the derivative of the cosecant of x is going to be the cosecant of x times the cotangent of x, but with a minus sign. Those are the four derivative rules. When we get to the inverse rules, that becomes messier, but we'll wait a little bit on that because these four are fine, they're useful. Let's do some examples. They're not going to be too hard, hopefully, but let's try it. The sine of x times plus 3 cosine of x. What is that, the derivative? Well, derivative of something plus something is the derivative of the first plus the derivative of the second. So it's going to be cosine of x plus 3 times minus the sine of x, or cosine of x minus 3 sine of x. And what about this one? I'll let you think about it for a second. We can do product rules on this, because it's the cosine of x times the cosine of x. So it'll be the derivative of the first, which is minus the sine of x, times the second, which is cosine of x. Plus, it's going to be exactly the same thing, minus that sine of x, plus times the cosine of x, plus the derivatives here. The derivative of the sine is the cosine of x times the sine of x, plus, now the derivative of the other one, which is the sine of x, its derivative is the cosine of x, times the sine of x. And if you do all of that, you notice something. They cancel out. You get 0. Now, getting 0 means that the function has a 0 slope. The function is this. A 0 derivative means your function's constant. So this is probably constant. And once I say that, maybe you already knew this. Maybe you were going like, why is he doing the slow way? Because there's an easier way. This, according to the basic rule, cosine squared of x plus sine squared of x is 1. And the derivative of a constant is 0. You wouldn't have had to do any of this if you remember that. On the other hand, it's nice to know, if you do it out really slow and long, you still get 0. Let's try one more, and then we'll call it a day. Find the line tangent to y equals the secant of x at x equals pi over 4. So what does the secant of x look like? Well, it's got vertical asymptotes in a lot of places, but where we're particularly concerned about is right there. I'm not sure exactly where it's going to hit down here, but that's what the tangent line is going to look like, clearly positive. And how do we find the tangent line? Well, we need the slope first, the tangent slope, which is the derivative. Well, it's the value of the derivative at that point. So we find the derivative. The derivative of the secant is, what? The secant times the tangent. So it's the secant of x times the tangent of x. And then we plug in pi over 4 to find our particular slope. Secant of pi over 4, tangent of pi over 4. Well, now you have to plug these values in. Hopefully you have a calculator or a good memory, but tangent of pi over 4 is 1. Secant of pi over 4 is the square root of 2. So we are faced with y equals the square root of 2x, put parentheses there just for avoiding confusion, plus something. We know that x is pi over 4. And we know that y is, well, let's give you what the secant of pi over 4 is, but we already knew that. I already told you the secant of pi over 4 is square root of 2. Square root of 2 is square root of 2 pi over 4's plus box. How do you cancel that all out? That's going to be, square root of 2 times, I believe, 1 minus pi over 4. Does that work? Yes. So our final answer is y equals square root of 2x plus square root of 2 times the quantity 1 minus pi over 4. Now let's think about that for a second. What are these values? Pi is about 3-ish. Pi over 4 is about 3/4 then. 1 minus that is about 1/4. This is about 1.4, so 1/4 of that is like about 0.3. So it looks like it really hits about here with a steeper than 1 slope. That seems pretty reasonable. This is some examples of the trig functions you can use and their derivatives, and hopefully it's helpful. Until next time.